In A-level mechanics, a lot of people drop marks with the modelling assumption questions, in particular the questions about strings and if the strings were not inextensible and if the strings were not light, that kind of stuff. Let's talk about it. You know, so these kind of things, right, where you've got like a connected trailer with a string or a rope in the middle, rope here, you've got like a plank here holding the rope up against the wall. So let's give you guys some advice. No strings attached. Haha, what a funny pun. Firstly, let's talk about this word taut. This word just means that the string is at its natural length. So the string is not like this, where the string is slack, right, and it's not fully extended. Taut means the string is extended to its natural length. Let's say you get a question where you've got A connected with B. A is driving forwards, right? And let's just say that the string is not taut, so in other words, the string is slack. And let's say the question was describe what would happen to the motion of B. Well, B is not going to move until the string is taut. So obviously A is going to drive forwards until the string has reached its natural length, and only then will B start to move. So B will have no acceleration until that string becomes taut. I mean, unless it's like some wind pushing B backwards, but as long as B is stationary, right, B is going to have zero acceleration until we get that string to be taut. And it's very similar in a rigid body question where you've got like a plank or a ladder here. The ladder is just going to slightly rotate around until the string becomes taut. So something similar to this, right? Now, the next word you see in these questions is light. The string is light, the rope is light. It just means that you assume the mass of the string is equal to 0. So again, let's say we've got a situation like this where we've got A connected with B, and A is going to be accelerating to the right forwards. And let's just say that that mass of this string is 0. So if that mass is 0 for the string, if we just assume again that the string is taut, as we said before, and also that it's inextensible, we'll come onto this in a bit more detail in a minute, but if that mass is 0, it just means that the tension throughout the string is the same at every position at any given moment in time. And so if the mass of the string is positive, so if the string actually does have some mass, then it means that the tension throughout the string changes as we move along the string. Now, the way to think about this is that the string is moving to the right because of course A is accelerating us to the right. So we've got a force here driving us to the right, we've got a resisting force going back against us. We'll call this T1, we'll call this T2. Now, hopefully we remember Newton's second law, F equals ma, okay? So we've got an acceleration. Now, the acceleration is constant throughout the entire system because the string is taut and it's inextensible. So that means that the entire system has the same acceleration. The mass, let's just focus on the mass of the string, okay? So the string's got the same acceleration as the system. The string has some kind of mass, and that's equal to the resultant force F. And that means that the resultant force T1 minus T2 is going to be equal to the mass of the string times the acceleration of the string, which is the same as the acceleration of the entire system, because again, what we mentioned here. So if we are going to be accelerating to the right, then obviously this acceleration is positive, okay? Obviously the mass of something is positive. So we got a positive number here. So that means that this T1 must be bigger than T2. So that tension there has to be bigger than this tension. So the tension is biggest here and lowest here. So T1 is bigger than T2. So as you go along the string, the tension is getting bigger and bigger. Maximum tension there, where we're being driven forwards, minimum tension back here. Now, if the acceleration is negative, then of course the roles are now reversed. If that is now negative, then that means that your resisting force T2 has to be bigger than T1, so that your resultant force is negative, right? So the tables turn, and now that would be your maximum tension, and this would be your minimum one. So basically, as you go along, the tension would decrease. So hopefully you can now appreciate that if that mass there is 0, then that means that T1 must be equal to T2, because then this whole thing there would be 0. So add the T2 to both sides, T1 equals T2. So that means that if you have a massless light string, then that means that the tension is the same across the entire string. Now, another consequence of the string having mass is actually the acceleration of the whole system. So imagine a situation where that string does not have mass. Okay, so you just have the mass of B plus the mass of A, right? If that string were to have mass instead, do you see how the mass of the entire diagram gets bigger, right? Because now there's a mass you have to add here. So if the mass of the entire diagram gets bigger, it means the acceleration of the entire system has to be smaller. So let's think about why that is, right? So the force of an entire system, okay, is equal to the mass of the entire system times the acceleration of that entire connected system. So divide both sides by m. If that m is bigger, right, so the bigger that number is on the bottom, the smaller the acceleration is, right? So if that string has mass, you've got the mass of B plus the mass of the string plus the mass of A. You've got a bigger mass. That m is bigger, the acceleration is smaller. So if the string does have mass, the acceleration of the whole system is smaller. But if the string does not have mass, then the acceleration doesn't account for the mass there, because of course there's no mass there. And again, very similar in this situation where we've got the plank in equilibrium, we've got the rope holding the plank in equilibrium. What would happen if that rope or that string did have mass? So you've got our string here. We now have a weight of mg, right? Because there is now mass. We obviously now have a weight. We've got the tension up here. We'll call this T1. So this tension at the wall. We've got the tension down here, T2, from the plank itself. That tension down there. Hopefully you can kind of see that it's obvious that now this T1 needs to be bigger than T2. So if that weight wasn't there, then obviously they're just the same, right? Because the string is in equilibrium, right? But if the string is to still be in equilibrium, because now we have this extra force here, this T1 needs to be bigger. So look, we've now got this extra component here. T2 plus this component needs to be equal to T1. So basically, the tension is going to increase. As we go up the rope, as we go up, the tension is going to increase. So minimum tension down there, increase, 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 maximum tension up there. Now the final word to watch out for with these questions is inextensible. Now an inextensible string means that the acceleration and the velocity is the same throughout the entire system at any given moment in time. And more specifically, the acceleration is a constant value throughout the entire journey. So the way to think about this, imagine that we start off here and then, like for example, 10 seconds later, we end up here along the road. Now again, that string must be a constant length, okay, because it's inextensible. So the left end of the string has moved this distance from there to there. We'll call that x1. And the right end of the string has moved from there to there. We'll call this distance x2. Now, because the lengths of the string are the same, it means that x1 must be equal to x2. Now, how do you go from displacement to velocity? Well, you have to differentiate. So differentiate both sides with respect to time. The velocities are both the same for this position and for this position there. And again, when you differentiate with respect to time again, you get acceleration, and the accelerations are clearly the same. So that tells us that the acceleration of everything is going to be the same, and it's going to be constant because that tension there and that tension there will be constant. And obviously you've got a driving force which is constant and a resisting force which is constant. All the forces are constant, so that means the acceleration is constant. Now, what if they asked you a question where they said to you, but the string is actually extensible? What does that mean? Now, this means that the acceleration of our system is not constant, and also that the velocities of A and B will be different. I mean, there could be a moment in time where they're actually the same, but generally speaking, they will be different velocities for both A and B. Now, the reasoning for this is actually beyond A-level maths. If you've done further maths or physics, you would have seen Hooke's law before. Again, we'll just say that the string is massless and it's taut, so initially it is at its natural length. If we apply a constant force D, because the string is extensible, we can extend the string. And we'll call that extension x, and actually as time goes on the extension will change, so actually this x is a function of time. It depends on time. Now, not all strings actually obey Hooke's law, but let's just say that this string does obey Hooke's law. What that means is that the tension that is trying to pull A backwards, this tension that A feels going against it, that tension will be directly proportional to the extension. Again, you don't need to know this for A-level maths, but that is just true for Hooke's law. So if the extension changes as time changes, then that means the tension changes as time changes, because tension is proportional to extension. So if you do F equals ma for both A and B, hopefully you can see that for A, the driving force, take away the tension, is going to be equal to the mass of A times the acceleration of A, and for B, the tension driving us forwards is going to be equal to the mass of B times the acceleration of B. Now, let's just assume that there is no friction here. Now, obviously, that D is constant, that mass is constant, but if the tension is changing, then obviously that means the acceleration there is changing, right? So A's acceleration is always changing, and also same with B, right? If that tension is changing for B, then obviously the acceleration must be changing for B as well. So the accelerations are not constant. So again, in general, in this situation, the accelerations would be different. I mean, it depends. Still watching this, I know you're going to do very well in your A-level maths, because I'm going to go through a very important mistake that I used to make as a student. Not say that the tension along the string changes as you move along the string. That is not true if it is extensible. It's only true if the tension has mass. Mass is the reason why the tension would change along the string, not extensibility. Hope that helps.